Hello there. Welcome to this video, which is dedicated to discussing a block cipher mode of operation. In this case, we will be focusing on output feedback mode, which is commonly abbreviated as OFB. This is presented by myself, Imran Shalabi. Outlining the content. In terms of this presentation, the following content will be discussed. It will be initiated through an introduction to block ciphers, and building on the introduction, output feedback mode will be introduced and discussed briefly. The encryption process, as well as the decryption process in OFB, can be thoroughly analyzed through stage-by-stage detailed animations. Last but not least, the advantages, as well as the disadvantages of using OFB will be discussed briefly. In cryptography, a block cipher is an encryption method that applies a deterministic algorithm along with a symmetric key to encrypt a block of text, rather than encrypting bit by bit as in stream ciphers. A deterministic algorithm is an algorithm which, when provided with a particular input, will always produce the same output. The machine always passes through the same sequence of states. Deterministic algorithms are by far the most studied and most familiar kind of algorithm, as well as one of the most practical, since they can be run on real machines efficiently and effectively. Symmetric keys are cryptographic keys that are used both in the encryption of a plain text and decryption of a ciphertext. And a block of text refers to fixed length groups of bits. The main types of block ciphers are data encryption standard, advanced encryption standard, and blowfish. For this particular case, data encryption standard will be used during the demonstration of the encryption and decryption processes of using OFB as a mode of operation. Block cipher modes of operations develop to eliminate the chance of encrypting identical blocks of text in the same way. Output feedback mode, commonly referred to as OFB, is a block cipher mode of operation that can be applied to any given block cipher. As in the cipher feedback mode, it allows the encryption of different sized blocks of text. However, there is a key difference between the two modes of operation. In OFB, the output of the encryption blocks is the feedback used as the input to the cipher in the next encryption block, along with using the same key, of course. Hence the name output feedback mode, whereby the output is continuously used as the feedback in subsequent encryption blocks. On the other hand, CFB uses the ciphertext as the feedback. OFB uses an initialization vector to ensure distinctiveness and randomness for higher security measures. Initialization vectors are blocks of bits used by mode of operation to ensure ciphertexts remain distinct, even when the same plain text message is encrypted a number of times. It is referred to as a nonce, meaning a number occurring once, since the encryption program uses it once per session at the initial encryption stage. It helps avoid repetition and the discovery of patterns, which helps protect against security threats and makes cryptanalysis significantly harder. In output feedback mode, all bits of the blocks are sent instead of selected S bits, unlike in CFB. It holds a great resistance towards bit transmission errors, and it also decreases the dependency of the ciphertext on its plaintext, which obviously enhances security. The following slide will discuss encryption in output feedback mode through a detailed dynamic stage-by-stage animation. During the encryption process, an initialization vector is generated with a specified number of bits. In this case, 64 bits of IV is used to initiate the encryption. Alongside the IV, a 64-bit symmetric key input is used to encrypt the 64-bit IV using a block cipher, such as Data Encryption Standard, or DES, which is a symmetric key block cipher implementation of a Feastal cipher. It is important to note that in cases where the bits do not match, padding is not required, unlike in some modes of operation. With that, a 64-bit encryption output X is generated. Here, X can signify the stage number or the cycle number. The encryption output X generated, along with the first 64 bits of plaintext, undergo exclusive disjunction, known as exclusive OR, which is a logical operation to yield 64 bits of ciphertext X. The encryption output of the first encryption cycle is the feedback used as the input to the block cipher DES alongside the same symmetric key in the subsequent encryption stage. It is important to note that the symmetric key is used as the same exact one on the previous stage with the same number of bits, and is the same block cipher used as well. As such, a new 64-bit encryption output x plus 1 is generated from this stage. The new encryption output, along with the subsequent 64 bits of plaintext x plus 1, are XOR'd together to generate the new 64-bit ciphertext x plus 1. The same process is cycled for the length of the plaintext. Therefore, if this were to continue, encryption output x plus 1 would be used as the cipher input, along with the same symmetric key and number of bits, to produce encryption output x plus 2, which would then be XOR'd with plaintext x plus 2 to produce ciphertext x plus 2, and this would continue so forth and so on. The common use of the encryption output of the previous stage as input in the next stage, along with the same key and number of bits and same block cipher type, as well as maintaining the same number of bits, ensures that the output feedback mode is implemented successfully. Decryption in OFB pretty much works the same way as the encryption process. During the decryption process, it practically follows the same structure and the flow of the encryption process. The key difference is that during the exclusive or logical operation process, in decryption, the ciphertext is used to yield the plaintext instead, while keeping the other factors involved identical to the encryption process, such as the key as well as the initialization vector used. And this ciphertext and plaintext replacement is carried on throughout every cycle across the decryption process. And this process is cycled continuously for the length of the ciphertext. That said, it is no doubt that using output feedback mode has a great implication in cryptography. A few advantages include the fact that it holds a great resistance towards bit transmission errors. A bit error in transmission will not multiply, as the error in one ciphertext block will only affect the current block's plaintext, since it's a stage-by-stage process. It also decreases the dependency of the ciphertext on its plaintext, which is an added benefit when it comes to security. The same plaintext message using the same key can be encrypted to produce different ciphertext. It also has a symmetrical structure of the encryption and decryption process. And the key stream used can be pre-generated, since it doesn't depend on the plaintext. The plaintext message length can be based on a random choice, which enables flexibility. And finally, it is not parallelizable, meaning the plaintext block can't be recovered from two adjacent ciphertext blocks, since the key is needed. Despite having the many advantages mentioned earlier, it also comes with its own set of disadvantages. The first being the fact that the sender and receiver of the message must be in sync during the encryption and decryption process, through access to the same IV and number of the blocks of output, which makes the operation inconvenient. OFB is also vulnerable to message stream modification attacks. Also, parallel operations can be implemented, and initialization vectors and keys must be regenerated every time. For a massive operation, this can prove to be inefficient. With that, this presentation regarding output feedback mode as a mode of operation is concluded. It has been a pleasure and very informative sharing this information with you. Until next time.